In this problem, we've got a gate or a dam that supports a channel of water, and we're trying to figure out the moment acting at the hinge at the bottom of this gate to support it. So naturally, there's a pressure force of the water acting on the gate in the clockwise direction, so we want to calculate the moment acting about the hinge in the counterclockwise direction. And the gate extends a width of b into the screen, and it's got a height. The height of the gate is the same as the height of the water, height a. Let's define a coordinate axis. We've got y equals 0 at the top, and it extends a length y below the surface of the water. The x-axis extends into the screen. It's a little bit complicated because if I draw a pressure profile from the top, the gauge pressure is a pressure of 0 at the top of it and some pressure down at the bottom. So if I drew this, I've got a pressure acting at any point or any depth y. So here's my pressure prism, pressure of 0 at the top, and it increases linearly with depth, or linearly with y. And because of this effect, instead of acting right at the centroid, the resultant force of the pressure acts a distance 2/3 of the way down from the top of the water. So if the total height of the gate is a, then the resultant force, we could call this distance yr. yr is equal to 2/3 a. And that means that this distance above the hinge is equal to a minus 2/3 a, or simply 1/3 a. To calculate the moment about the hinge, I need both the lever arm, in this case 1/3 a, and the magnitude of the resultant force. If I look back at the pressure prism, the magnitude of the resultant force, Fr, is equal to the average pressure times the area of the gate. And because it's a linear pressure profile with the pressure of 0 at the top, and increasing linearly, the average pressure is a pressure acting right at the centroid, and in this case of a rectangular gate, the centroid is a value of a over 2. So I can say we'll call this hc, the depth of the centroid, is 1/2 a. And the average pressure in that case is simply the depth of the fluid at the centroid times its density times h. So here I've got rho of the fluid times hc times g times the cross-sectional area of the gate. And the cross-sectional area of the gate is simply the height of it times its depth into the screen, or in this case a times b. And if I plug in hc is equal to 1/2 a, I've got 1/2 rho g a squared b is the magnitude of the resultant force. And finally, to calculate the moment, the moment is simply the magnitude of the resultant force times this distance from the hinge, which is 1/3 a. And with the clockwise rule, or the right-hand rule, a negative sign is used to indicate a clockwise moment of the fluid acting on the gate. So then substituting in for Fr, I get negative 1/6 rho g a squared b. I can also calculate the moment by integrating directly. So if I say the moment is, I'll use again the negative sign for a clockwise moment, negative times some distance a minus y. So if I've got a force that's acting a distance y from the surface of the water, I've got a distance of a minus y from acting a distance a minus y above the hinge. So I'll say the integral of a minus y times f times a differential surface area. So here I've got I'm integrating over the area of the gate. I'm taking the lever arm multiplied by the force. I take the lever arm multiplied by a differential force. And this differential force, if I continue with this, a and a minus y is simply p times the differential area. And continuing with this, I've got negative the area times, again, a minus y, the lever arm, times rho g y dA, where rho g y is the static pressure at some value y below the surface. And if I pull the negative rho g out of the integral and I'll integrate from a distance 0 to b into the screen and 0 to a above the gate times, again, a minus y times y dy dx. And I'll let you evaluate this integral on your own, but when you go through it, you'll get a value of negative 1/6 rho g a squared b, just like we did using the rule of thumb. And thirdly, a third way to get the same answer is if I set it up again with the resultant force acting some distance yr from the surface of the water, and I use this expression where yr is equal to the second moment of the area, ixc, over yc times a plus yc. For a rectangular gate, I know that ixc is equal to 1/12 ba cubed. And this is an expression that's tabulated, and it depends on the geometry that you're looking for. In this case, we're looking at a rectangular gate, so this geometry is given to us. And the centroid of a rectangular object acts right at the geometric center of it. So we've got YC, this distance right here, is equal to A over 2. So distance, again, half the height of the gate below the surface of the water. So if I plug in, I've got YR is equal to 1/12 BA cubed, and it's divided by 1/2 A, the centroid, times the area, which is A times B, plus 1/2 A. And if I simplify this, the B's cancel out, and I've got A in the numerator, and this equals 1 over 6 times A plus 1/2 A, and that's equal to 2/3 A. So again, the moment is equal to negative FR times A minus YR, and like we've shown before, FR is negative 1/2 rho G A squared B. And A minus YR now is simply A minus 2/3 A. And again, what we come up with is a value of negative 1 over 6 times rho G A cubed B.